We've been talking a lot about heat transfer, but how does heat transfer? There are three different ways. Conduction is heat transfer through stationary matter by physical contact. For example, we have the heat transfer between electric burner of a stove and the bottom of a pan, and this is by conduction. The second method is convection, which is the heat transfer by macroscopic movement of a fluid, such as in forced air furnace, so the movement is gas, and then in weather system, that's also a movement of gas, or this port, when we have the water move inside. A third method is called radiation, which occurs when microwaves, infrared radiation, visible light, or another form of electromagnetic radiation is emitted or absorbed. In this example of a fireplace, heat transfer occurs by all three methods. We have radiation, responsible for most of the heat transfer into the room. Heat transfer also occurs through conduction into the room, but at a much slower rate. Heat transfer by convection occurs through cold air entering the room around the window and hot air leaving the room by raising up the chimney. For conduction, a temperature difference causes thermal energy to flow from hot to cold when systems are in thermal contact. These are some examples of good conductor of heat, and these are examples for bad conductor of heat. Here is a molecular picture of heat conduction. There are two bodies at different temperatures, T hot and T cold. The average kinetic energy of a molecule in the hot body is higher than the colder body. If two molecules collide, energy transfer from the high energy molecule to the low energy molecule. So the rate of heat transfer increases with increasing temperature difference. Delta T equals to T hot minus T cold. If the temperatures are the same, the net heat transfer rate would be 0. Besides, because the number of collisions increases with increasing area, heat conduction is also proportional to the cross-sectional area, and this is the second factor to determine the heat transfer rate. The third factor is the distance. The greater the distance between hot and cold, the more time the material takes to transfer the same amount of heat. If we consider all these three factors, the rate of conductive heat transfer through a material can be expressed as Ka T2 minus T1 over D, where this K is thermal conductivity of a material, determines how quickly it can conduct heat. And T2 minus T1 is the temperature difference. A is the cross-sectional area or surface area. D is the distance or thickness of the material. And the unit of this rate of heat transfer is joule per second, or is the same as volt. Here are some data of the thermal conductivity of different materials. Now we can rethink about this question and explain it using the concepts of temperature, thermal equilibrium, heat transfer, and conduction. You may choose your answer on the sidebar. Let's look at this example together. Now we also have an icebox, but this time we are not considering the icebox as an ideal calorimeter as before. There is a net heat transfer between the objects in the icebox and the environment outside, determined by the rate of heat transfer by conduction. In the icebox, the temperature is always kept at 0 degrees Celsius, and the environment temperature is always 35.0 degrees Celsius, so that the rate Q over T equals to the thermal conductivity of the material times the surface area of the icebox times the temperature difference divided by the thickness of the icebox. And we get 13.3 joule per second. For 1 day, we have the total heat needed to be 30.3 joule per second times 86400 seconds, and we get 1.15 times 10 to the power 6 joule. This amount of heat needs to be balanced by the heat absorbed from melting ice, so that the mass of the ice melts in 1 day should be Q over L sub F, and we get 3.44 kilogram of ice. Convection is driven by large-scale flow of fluid, either liquid or gas. It is the main method of heat transfer for liquids and gases, and it is usually more complicated than conduction. For example, in this port, some water is heated by the bottom of the port, and its volume expands, density kind of decreases a little bit, and the hot water begins to rise. We have cooler water up there, and the cooler water has a slightly bigger density than the hot water. So the cooler water sinks to the bottom, and it gets heated again by the bottom of the port. So it forms this kind of convection. And finally, the water inside the port gets all heated. This is an old German apparatus which uses natural convection. It has these candles to heat the air from the bottom. The hot air rises so that the fan begins to rotate. We also have this kind of convection oven, which has forced convection inside the oven to heat up the food. A cold wind is much chilling than still cold air, because convection combines with conduction in the body to increase the rate at which energy is transferred away from the body. Wind chill factors are a dramatic reminder at convection's ability to transfer heat faster than conduction. For example, a 30-mile-per-hour wind at 30 degrees Fahrenheit has the chilling equivalent of still air at about 15 degrees Fahrenheit. Although air can transfer heat rapidly by convection, it is a poor conductor and thus a good insulator. The amount of average space for airflow determines whether air acts as an insulator or conductor. Fur takes advantage of low conductivity of air by trapping it in spaces too small to support convection, so that fur is a very good lightweight insulator. On the other hand, water is a much better heat conductor than air, and lateral convection occurs more easily. If we compare the case of air with water, the expected survival time in 45 degrees Fahrenheit in air could be days, but the expected survival time in 45 degrees Fahrenheit in water is only 1 to 3 hours because the body loses heat much more quickly in water. Some interesting phenomena happen when convection is accompanied by a phase change. It allows us to cool off by sweating, even if temperature of the surrounding air exceeds body temperature. Let's look at these examples together. The energy needed for evaporating sweat is Q equals to m L sub V, because there's a change from the liquid form, which is water, to the gas. So that the energy lost per unit time should be Q over T. And since we know the person produced heat at a rate about 120 volt, this rate should be equal to 120 volt, which is 120 joule per second. Then we can get the latent heat of vaporization, L sub V, is 2430 joule per gram, so that the mass evaporated per unit time should be this 120 over this L sub V, and we get 0.0494 gram per second, which is the same as 2.96 gram per minute. You can feel that the heat transfer from the sun. The space between Earth and the sun is largely empty, so the sun warms us without any possibility of heat transfer by convection or conduction. This heat transfer is actually by radiation. All objects can emit electromagnetic waves which carry energy with them. Different names are used for electromagnetic waves of different wavelengths. We have radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. We have the experience that the hotter an object is, the higher the energy of the emitted electromagnetic waves. This is a graph of the spectra of electromagnetic waves emitted from an ideal radiator at 3 different temperatures. The intensity or the rate of radiation emission increases dramatically with temperature, and the spectrum shifts toward the visible and ultraviolet parts of the spectrum. The rate of heat transfer by emitted radiation is determined by this Stefan-Boltzmann law of radiation, where sigma is the Stefan-Boltzmann constant, A is the surface area of the object, and T is the temperature in absolute temperature in Kelvin. The symbol E here stands for the emissivity of the object, which is a measure of how well it radiates. An ideal blackbody radiator has E equals to 1, whereas a perfect reflector has E equals to 0. Real objects have E between 0 and 1. The radiation rate is directly proportional to the fourth power of the absolute temperature, and that's a remarkably strong temperature dependence. Even a very small temperature variation can be detected because of this t to the power of 4 dependence. These images are called thermographs, and it can be used medically to detect regions of abnormally high temperature in the body. Let's look at this example together. According to the equation of the rate of heat transfer by radiation, we can plug in the values of T1 and T2. We have T1 equals to 306 Kelvin and T2 equals to 295 Kelvin. Then we get the rate of the heat transferred by radiation of this unclothed person is the coefficient times 0.97, that's the emissivity of the skin, times the total area, surface area of the person, times the temperature difference, but to the power of 4. And we get minus 99 volt. Radiation is also very important for the relationship between the Sun and the Earth. The Earth receives almost all its energy from radiation of the Sun and reflects some of it back into outer space. Because the Sun is hotter than the Earth, the net energy flux is always from the Sun to the Earth. To balance energy from the Sun with the energy radiated by the Earth temperature should be minus 30 degrees Celsius. The often mentioned greenhouse effect is a natural phenomenon responsible for providing temperatures suitable for life on Earth. Most of the infrared radiation emitted from the Earth is absorbed by carbon dioxide and water in the atmosphere and then re-radiated back to the Earth or into outer space. Re-radiation back to the Earth maintains a surface temperature about 40 degrees Celsius higher than what it should be if there was no atmosphere.